provide the lecture with this black whiteboard. Okay. So today, the thing I have to introduce you in, you already know, we already learned about this. Okay. So here, this is the entire deep architecture. Okay. So can you see this? Okay. And let's say this is the initial input image, and this is the final output y. Okay. And then we have to calculate the distance between ground truth and our predicted value. Okay. And via this, we have to calculate the loss. Okay. And in previous lecture, I said inside the entire deep architecture that have multiple layers, there are multiple layers stacked inside the deep architecture, right? Okay. So here, 1, 2, 3, 4, 6 layers are stacked. Okay. And for example, let's say this is the first layer and having sector as the parameter. Okay. And let's say this is the y1. Okay. And this is the second block, their intermediate output is y2. And this y3, y4, y5, and then we will get y. And their parameters, we will call them as sector. So the large sector is concatenation of all the 6 sectors, right? Then, when initializing this entire deep architecture, these sector values are randomly initialized, okay? Because of that, our predicted value y will be random, and that will be far from the ground truth y, okay? But we have to learn our parameter sector to make our y close to y ground truth, okay? And for doing that, I mentioned that we have to define 2 gradients for each layers inside the entire deep architecture. That is actually d y1 and dy1 d sector 1. So this was the differentiation of for this layer, we have to get differentiation of y, their output, respect to their input. That's dy1, d sector 1, right? And also, we also have to have dy1, di, which is the differentiation of their output, respect to their input. Okay? And also, for the second layer, we have to have these 2 things. The output differentiation of output y2 respect to the input y1. Okay, that's this. And then differentiation of output y2 with respect to sector 2, which is the parameter. Okay. We have to define these 2 gradients for each layer, and I mentioned that is for actually finding DLD sector, and sector here means the large sector. Okay? So we have to, so this is actually concatenation of differentiation of the L with respect to all the parameters inside the deep architecture. Okay. For example, I will show you how we can calculate this and this. Okay. Okay. So this is the differentiation of L, which is the last layer output with respect to this. Okay, so that could be represented like this via the chain rule, right? So loss L is obtained, their loss L and sector 6, their relation is, I mean, indirectly, uh, formulated by this Y. So the loss L's differentiation respect to the parameter sector 6 is can be represented as this multiplication. Okay, and this we already defined that. Okay, here we have to define these two values for this layer. So this is already defined value, and we can also differentiate this value. Okay, so to get dl dy. So dl d sector 6 can be defined, okay, via the chain rule. So if this layer is having this, and also this loss calculation layer is having this, then their multiplication becomes this. Okay, that is also exists. Okay, so we can get this. And also, next, DL d sector 5, okay, for this, the differentiation of last loss with respect to the second last layer, sector 5, the fifth layer, uh, their parameter sector 5, can be obtained by sorry. Okay, can you see this? Okay. So this was already exist, and this is the differentiation of these respect to the input for the sixth layer. So this is the differentiation of sixth layer's output respect to the sixth layer's input. Okay, and this last term is the differentiation of fifth layer's output with respect to the fifth layer's parameter sector 5. Okay, and actually this is coming from two values of this layer. Okay, are you guys following this? Okay, anyways, if each layer is having these two gradient, we can gradually get DLD sector for every layer. Okay, 이거 이해됩니까? 이해돼요? 뒤에? 이해 안 되시는 분? 되게 중요한데. 그러니까 sorry for foreigners. 이거 6개 레이어가 각각 세트가 다 있고, 그 다음에 각각이 이 두 개의 그라디언트가 있으면은 뒤에서부터 이제 생각을 하면은 맨 마지막 로스가 각각의 레이어, 6개 레이어의 파라미터에 대해서 다 미분한가, 요거를 구하면 이거 왜 구해야 되죠? 그라디언트 디센트에서 얘 쓰면은 업데이트 할 수 있으니까 구하는 거잖아요. 그러니까 얘 각각 하나를 그냥 각 레이어가 요거 두 개가 있으면 예를 들면은 이 L을 얘에 대해서 미분한다. 그러면은 로스 L을 얘에 대해서 미분한 거 곱하고 얘를 인풋에 대해서 이 레이어의 인풋에 대해서 곱한 거 미분한 거 곱하고 그다음에 얘를 얘에 대해서 미분한 거 곱하고 얘를 얘에 대해서 미분한 거 곱하고 얘를 얘에 대해서 미분한 거 곱하고 마지막에 얘를 얘에 대해서 미분한 걸 곱하면 L을 세타2에 대해서 미분한 거를 바로 구할 수 있잖아요. 체인 룰에 의해서. 알겠나요? 그러니까 각각의 레이어가 다 어떻게 보면 이 두 가지가 있으면 이 전체 딥 네트워크에 대한 요거를 다 구할 수 있으니까 이제 요거를 구하면 뭘 하냐면 섹터를 업데이트 할 수 있잖아요. 이렇게. 그래서 각각의 레이어가 미분 가능하다는 게 중요하다는 거 이해됩니까? 근데 하나가 더 여기서 살짝 이제 예외랄까? So there's one exception. I mean, if some layers, some intermediate layers can uh, not have, can omit this sector four. I mean, some layers in the entire deep architecture uh, can, what to say, omit this sector four. I mean, it cannot contain some parameters, but still for that specific layer, if their gradient for the differentiation of output with respect to their input is defined, then they can be also used in the entire deep architecture. Okay? So because, DLD sector 4, if there is no sector 4 in the entire deep architecture, then we cannot get this. But we will not update the sector 4, so it is not required. At the same time, for calculating previous layers differentiation, DLD sector 2 or DLD sector 3, the thing we only need is this, right? Okay. So we do not need DL sector 4 for calculating DL previous layers differentiation. Okay. The only thing we need is this, okay, for this fourth layer. So if some layer in the entire deep architecture, if it is not having parameter, then but still this differentiation of that layer's output with respect to their inputs are defined, then that can be usable in the deep architecture. 이게 저번에도 이래서 랩탑을 바꿨는데도
스크린이 지금 안 올라간다는 말씀.
아니요, 이게 연결이 안 HDMI
저희가 아니 잘못 접수가 돼서
HDMI가 연결.
전원 꺼진 거 아니에요?
전원이 안 돼.
이게
네, 프로젝트가 지금 켜지고 있어.
입장은 전화 네, 해보세요.
Okay. And the other thing you have to remember is if some function f is constituted with this type of operations, if you make some function using these four operations to output y from the input x, okay, then every polynomials that is, this equation is polynomial, right? Then, and also every polynomial can be differentiated with respect to their input x, okay? So if you constitute these four operator to make the function f, those every functions are that functions are differentiable, okay? And every every layer that is based on this function can be usable in the entire deep architecture. Okay. 혹시 이전 수업 들은 사람 됐나요, 이거? 바로 됐어요. 그래서 모든 4차 연산으로 이 플러스 곱하기 나누기 곱셈으로 인풋을 넣어서 아웃풋을 뭔가 만든다면 모든 다항식은 미분 가능하잖아요. 고등학교 때 배웠죠. 그래서 그런 연산으로 된 모든 레이어는 사실 우리가 썼던 리니어 레이어, for example, that is also composed of multiplication and addition operator, right? So this is differentiable operator and can be used in the deep architecture, okay? Okay. And the sixth page, I'm showing that every given some x and y, this is, for example, in the computer vision domain, this is the RGB image. The input is normally the RGB image, and the y is the for classification part. This is the semantic label, right? For example, cat, dog. Okay. Any differentiable layers can be located here. Okay. And if we collect many x and y pair, okay, and then using some appropriate loss function and using the gradient descent, we can make this any differentiable function to work to predict some output which is close to our ground truth. Okay? 이거 이해됩니까? 돼요. 이거는 반응이 적은데 아까보다 아닌가요? 그러니까 X랑 Y가 있으면 X는 RGB 이미지겠죠. 컴퓨터 비전 도메인에서는. Y는 어떤 뭐 분류하는 타스크면은 뭐 캣이나 도그나 어떤 뭐 시멘틱 클래스겠죠. 우리가 원하는 맞나요? 이 중간에 디퍼런셔블 레이어가 있으면 디퍼런셔블 레이어라는 거는 그것의 아웃풋이 인풋으로 미분 가능하고 아웃풋이 중간에 있는 모든 섹터에 대해서 미분값을 구할 수 있는 레이어를 우리가 정의를 하면 그런 펑션으로 구성된 어떤 미분 가능한 레이어가 중간에 와도 사실은 다 학습할 수 있다는 거예요. 어느 정도는 로스 펑션만 잘 정의하면 우리가 데이터를 XY 페어를 뭐 한 10만 장 모으고 하면 요 섹터를 학습을 할 수가 있다는 거죠. 성능이 문제지, 사실은. I mean, the accuracy, it could be a problem. So we can, anyways, I mean, to make this sector to output, I mean, close to the ground truth, I mean, for many samples. But I mean, because of the, how to say, depending on this, what type of differentiable layers we are using, that actually makes the, I mean, changes in the accuracy. But anyways, the parameters are getting smarter and it is, I mean, better than random, right? But their maximum accuracy could be bounded by which differentiable operator we are using, okay? And one of the successful operator that could be used in this differentiable layer is the convolution operation. Convolution. Have you heard about convolution operation before? I mean, please raise your hand if you already heard about this convolution operation. So in which class have you learned about this convolution operation? Do you remember? AIP2. Or have you took any signal processing, random process? Have you take that course? Okay. Is there anybody who took the signal processing course? Maybe not. I mean, convolution operator, this is the widely used, how to say, operator that could be applied to some one-dimensional and also the two-dimensional or other dimensional signals. When processing this diverse form of the signals, I mean, we are using this convolution operation. So maybe you have heard about filtering operation in Photoshop, right? Have you heard about that? So please raise your hand if you heard about filtering operation in the Photoshop. 필터를 건다 이런 표현 들어본 적 없어요. 영상에 필터를 건다. 들어본 적 있죠? So, I mean, in Photoshop, we can apply some blurring filter or sharpening filter to make, images blurred or to make the images more sharpened. Okay, we can apply some filter in the Photoshop, and applying that filter is actually applying convolutional operation on the image using some corner functions. Okay, so I will explain that. Okay, further. Before deep learning, this convolution operation is widely used for processing one-dimensional signal like audio signals or other form of the one-dimensional signal at the same time for processing image signals or video signals. Okay? We can make images sharper by designing filters as the sharpening filter. Okay, and we can apply, we can make images blurred by design this convolutional filter to have the blurred coefficients. Okay. Anyways, you are already familiar with the thing I want to tell you here is you are already familiar with convolution operation because you are using that when you edit your photos in the Photoshop. Okay. The convolution operation, actually, I made a slide for that in page 8 of the material. I mean, their operation is actually composed of plus and multiplication. Okay. So here, let's say we have 3 by 3 image. Okay. In pixels, we can have some values from 0 to 255. Each pixel can have this range of pixel value. Okay. And let's say this has some pixel values like this. Okay. Okay. And let's say we are having some 2 by 2 dimensional colors. Okay? So their coefficients are like this. Okay? And when applying this 2D convolution operation in this image, this is the image, and this is the color, or we call it as filter, corner filter, or filter corner. So what we do is we first locate this filter corner in this location. And what we do is multiplication between elements. Okay, so these pixels are multiplied with this. Okay, and this pixel is multiplied with this. This is multiplied with this. This is multiplied with this. It is, if we locate this filter corner in this area, okay, so that's why we element-wise multiply each element, okay? And then we first, multiply each element, and then we add them, okay? And this value becomes the first output value. Okay. And then next thing we do is we slide this window to right and do the same for next. And then that becomes the right pixels of the output. Okay. Are you guys following this? And then we there's no right pixel anymore, so we move it to here, okay, and do the same to output this pixel, output pixel. Okay, are you guys following this? And then we move the window to the right again and do the same to calculate the next pixel. Okay. Are you guys following this? I mean, this is the output of the convolution. Okay. Then, as I told you, every operator, I mean, this filter corner coefficient ABCD is the parameter sector actually. This is the value we have to learn through the training. Okay. And then this is some input. Okay. And this is the actually the function f that can map input to the output. Okay. Then here, every operation is composed of multiplication and addition. So we can differentiate the output with respect to the input image. Okay. And also at the same time, we can differentiate this output with respect to the sector, which is the corner filters coefficients. Okay. Are you guys understanding this? Okay. So any differentiable layers could be located between the input and output, right? But the convolution was widely used for processing the images already. At the same time, they are differentiable, okay? So the computer vision researchers are motivated to use convolution operation inside the deep architecture, okay? And indeed, they found that this works very good. Their accuracy, I mean, when predicting this Y from the image, they observed that their accuracy is very good. Okay. So in the material, page 14, I mean, page 8 through 13, I explain about this operation, right? And in page 14, this is the example of image blurring. So if we constitute the filter corner values as 1, okay, then when outputting the output pixel, in the input pixels, nearest neighbors values are averaged. Okay. So are you seeing the page 14, right? So when applying convolution on this input image using the filter corner having all 1 values, when I mean the output, when calculating the output pixels, the nearest pixels values are averaged, and because of that, the effect is if humans see that output image, we feel that images become blurred. Okay. Okay. And you can define different types of filter. For example, for sharpening, you have to define different styled coefficients, okay, to make the images sharpen. Okay. Anyways, we will learn these filter coefficients of the convolution operation to properly map image pixels to some semantic classes eventually. Okay. 네. 예, 예, 예. 그러셔도 되고. 이거를 윈도우로 바꿔도 안 되네. 근데 적어놓은 시간은 됐거든요. 저기. And another thing I have to tell you is there are some actually parameters for this convolution operation. So as you see here, the input image is 3 by 3, right? And the output image, that's 2 by 2, okay? 1 pixel reducted, okay? That's the characteristic of the convolution operation. Okay? But sometimes you want to remain the size of the output same as the input image, right? In that case, you can have zero around the input image. And then calculate this same convolution operation. Then the output will be magnified, slightly magnified. Actually, this scheme had some zero around the original input image. That's called as zero padding. Okay, that's explained in the page 15. Okay. Also, the thing I have to tell you is here we slide the windows by 1 pixels. Okay? In default to the convolution, we slide the windows by 1 pixel. But we can change that to have rather than 1 pixels. Okay? That is actually called as stride. Okay. So if stride, this is the situation where stride is 1. Okay? If the stride is 2, then we will slide these windows, the corner window by 2 pixels. Okay. Then, as a result, the output map will be reduced. The size will be reduced. Okay. Are you agree with this? So actually, there are one formula that can decide the output size from the input image size. 디스플레이 되나요? 네, 해도 되죠. So this is actually the formula that can decide the output map size from the input map size. This is the zero padding, number of zero padding. Okay. So default padding was 0, right? 네네. 이게 복제로 돼 있어서 그런가요? 아니요, 복제로 안 돼 있고 얘로만 돼 있었어. 알겠습니다. 네, 감사합니다. So finally, 네. 네. Okay. So this is the 2D convolution operation, okay? And this is the zero padding, okay? So if we make these zeros around the images, then the output size is becoming larger, okay? And yeah. And actually, that is the formula that can map input size to the output, okay? And also, this is the stride. So, previously, if we apply convolution by moving this window by 1 pixels, okay, then 3 times the output can be generated. But if we set the stride as 2, then now the windows will move by this, okay? by 2 pixels, okay? And resultant output will be reduced, okay? That is actually explained here, okay? So I guys understand what is 2D convolution operation is, right? And the coefficients, the filter corners for coefficients that becomes parameter sector, okay? Are you guys following this? Okay. And this is this was the convolution operation I explained before, but actual layer that will be used in the CNN, the convolutional layer is slightly different from the convolution operation itself. Okay, so I will explain the difference. Okay, so they are actually mapping, making some map. So this is one, how to say, channels of the original image. Okay, first channel, and this is the second channel, and this is the third channel of the image. Okay, and that is, we are assuming that those image size is 5 by 5. Okay, and let's say we are applying filter corner with 3 by 3 size. Okay, and we will apply first, let's say input image is having 3 channels. Okay, normally for our color images, we have 3 channels: R channel, which means red channel, green channel, and blue channel. Okay, the original RGB image that is having 3 channels. Okay, and for each channel, we are applying this filter. Okay, and we will output this output map by anyways using the convolutional 2D operation. Okay, are you guys following this? Okay, and the thing we will do after obtaining these 3 output map from the 3 channels of the input, we will now add the 3 output channel, and that actually becomes the first channels of the output. Okay, are you guys understanding this? This is easy, right? So this is the 2D convolution operation. By applying the filter kernel, we can obtain 3 output map, and then we we add them to obtain the final output map, their first channel. Okay, and if we do the same for using different kernel, and then if we again add them, we can get the second channel of the output map. Okay, and by iteratively doing this, we can get n number of output channels. Okay, so I mean, the thing which is changed is here is you can see here the index of this filter map is F11, meaning these filter kernels are mapping first input to the first output channel. Okay, and this means mapping the second input channel to the first output. Okay, so this is O2, but I mean this index is meaning this output index, output channels index. Okay, so this is meaning first channel of first output, and this is second channel of first output, and so on. Okay, so and then the next thing, we define this filter kernel their index as 1 to F12, meaning that we will map this first input to the second input, second output. Okay, and this is also meaning this filter F22 is mapping the second input to the second output. Okay, so by adding some filter kernels, we can define multiple output channels. Okay, given this fixed number of input channels, by adding few filter corners, we can define the output channels as we desire. Okay, we can freely design n number of output channels. Okay, by adding n number of by adding more filter corners. Okay, so if the input channels, if there are how to say n number of output channel and n number of input channels, there are n by n number of filter corners required. Okay. So if there are n number of input channels and there are, if there are n number of output channels, in the middle, there should be n by n number of filter corners required. Okay. Are you guys following this? This is easy. Okay. So just adding this intermediate to calculate the final channels of the output map. Okay. So by defining, as I mentioned, m by n, let's say this is m, okay? M by n number of filter corners, we can map inputs to the output having m channels input and n number of output channels, okay? This is the convolutional layer. Inside the core operation, this is convolution, but we have some more modules, okay, to actually constitute this convolutional layer, okay? But that is not much, okay? Anyways, this is the convolutional neural network architecture. So this is the initial input image, and this is our final output. But in between that, this operation is meaning the convolutional layer that we just learned, okay? And there are actually few more operator called as pooling and also activation. So we will further learn about that. And fully connected layer, it is this kind of operation, okay, that we already learned. And actually the same as MLP. So fully connected layer, that is actually same as MLP layer, multi-layer perceptron. That is the layers that stack linear layers, okay, with the nonlinear layer in the middle, right? So fully connected layers, and then we will map finally we will map this 2D image to the one-dimensional vector that is actually representing the probability for each semantic class. So let's say there are 10 semantic objects, then our final vector should be 10-dimensional vector, okay, to represent their probability, okay? Are you guys following this? Okay. And how to say, the first part, you have to remember that the first part, they are applying convolution operation. So for example, here, their image size is, for example, normally we use 2 to 4 by 2 to 4 dimensional image as the input. And by applying convolutions, we saw that is reducing the dimension of the images, okay? So you can see their dimensions are slightly reduced, okay? And after some convolutional layers, their dimensions are almost becoming close to 1 by 1, but not exactly 1 by 1. We actually flatten them, okay? So here, what happens is applying some flattening operation. So for example, here, let's say their two dimension is, let's say, 3 by 3. If we originally it was 2 to 4 by 2 to 4 to the image, but by applying convolution operation multiple times, we can reduce it to 3 by 3, okay? And then let's say the channel numbers are, for example, there are 128 dimensional channels. Okay. Then this is the output, for example, here. Then we can, by applying this flattening operation, we can make two-dimensional dimension into one by one. And we can, I'm not, let's say this is D, then anyways, we are making some D-dimensional vector at some point by flattening that, okay? And then we apply MLP layer, which can process one-dimensional signal, okay? So this, for applying this type of operation, the X value should be one-dimensional vector. Are you guys following this? Okay. So, so for doing that, we actually applying some flattening, and then initially their dimension is quite high. This was the D-dimensional vector, and then slightly reduce it, for example, to D divided by 4 dimension, and eventually we map it to 10-dimensional vector that is representing the probability for 10 classes, okay? Then you can see the convolution operation is differentiable, right? And the MLP layers are differentiable. So entire architecture in between this input and output is now becoming differentiable, okay? Then every parameters in the middle can be updated via the gradient descent, okay? Okay, are you guys understanding this? Okay. Okay. And also in the PyTorch, you can just use this torch.nndet com2D function to implement 2D convolutional layer. Okay. So in there, you can specify the input channels. For RGB image, it should be 3, but for grayscale image, it should be 1. Okay. And output channel, we can specify that. Okay. If we have more than one n output channel, then we can define n number of filter corners. Okay. And this is meaning the filter corner size, 3 by 3 filter, we can specify that. Okay. So, and also we can decide padding number, and also there are parameters for stride as well. Okay. So stride, padding, corner size, that decide the output map size. Okay. We can actually freely design the output map size by controlling this corner, padding, and stride. And also we can freely design their output channel number directly by controlling this number. Okay. So you can implement convolutional 2D using this one line of code in the PyTorch, okay? And for example, if there are 3 input channel, then you have to specify that as 3, okay? And if the output channel, if you want to make this O4, want to design output as having the 4 channels, then you have to specify it here. And you can specify the corner size and padding number and also the stride, okay? And another thing I have to tell you about is this pooling layer, okay? This pooling is another frequently used operator in the CNN architecture. What it does is basically doing some downsampling. Okay. So let's say there always have to have this pooling always have to have this hyperparameter, okay, which dimensional pooling, okay. For example, if this is 2 by 2 pooling, then it will downsample the original image by 2 times. Okay. So what it does is let's say that is 4x4 image, then if it is 2x2 pooling, and if you set there's tried as 2, sorry, their window become this 2x2, okay? And this window is moved by 2 pixels because tried is 2, okay? 2, 2, okay? And then what you will do is you will, how to say, pick one value from each window, okay? So in each window, you will pick just one value from each window, okay? As a result, by applying pooling, your 2D images are also reduced, okay? Their dimension is also reduced. But which method you will use for picking just one pixel from this window is actually varied, okay? But widely used technique is max pooling and average pooling. So max pooling, it is selecting the largest entry in each window, okay? And average pooling, it averages all the pixels inside the window, okay? But, and for each pooling, you can use the PyTorch functions already implemented. But here, which is important, this is very easy to follow, right? Pooling is just picking one pixel from the window, okay? But you have to understand why this is differentiable, actually. So, so if you picking this value 20, for example, in the max pooling case, if you pick this 20 out of these 4 values, it is it is actually same as multiplying 0 to this value and multiplying 1 to 20. Okay. And also, picking largest value out of this 4 to make this 1 pixel is multiplying 0 to other values and multiply 1 to this largest value and adding them, okay? So because of that, the output is still differentiable with respect to the input and also their parameters, okay? And there should be that kind of mask multiplying 1, 0, 0, 0, 1, 0, 1, 0, 0. This type of mask should be retained in somewhere, okay? If that mask is retained, then, this operation, the pooling is differentiable with respect to their input and their mask values, okay? And another thing is, in the pooling, there is no sector. There is no sector to learn, okay? But still can be usable in the deep architecture. The thing they have to define is the differentiation of their output with respect to their input. Okay, if that is defined, as I told you before, it can transmit the how to say gradient from the last part to the first earlier part. Okay, so the entire architecture is still differentiable. Okay, and for example, for average pooling, the output values are averaged by these 4 values, okay? So they are also differentiable, okay? Okay, so they could be used in the entire deep architecture, okay? Are you guys following this? Okay. And another thing widely used inside the deep architecture is samely as before. When I explain about this MLP, I say about the sigma function. Okay, without this sigma, the entire MLP converges to a huge linear layer. Okay, so similarly in convolutional operation, this plus multiplication and addition operation, the convolution is mainly constituted with this plus and multiplication operations. Okay, this is actually linear operation, so they cannot solely represent some nonlinear mapping between the input and output. So because of that, in CNNs, they also use nonlinear activation layers in between the convolutional layers. Okay, and these three functions are widely used actually. Okay, so I will, but nowadays this is, I mean, having good characteristic. So we are now frequently use this ReLU instead of this sigmoid or tangent hyperbolic. But anyways, uh, I will show you what is the activation layer. So uh, because thanks to this kind of curve, differently to this type of linear function, they can give some nonlinearity to the entire architectures if they are used in the middle of the layers, okay? And the characteristic of this sigmoid is their x values are lying on minus infinity to infinity, okay? But their y values are bounded to 0 to 1, okay? So you can see their y values are bounded to these two straight lines, okay? This is the characteristic of the sigmoid function. And therefore, I mean, formula is like this, okay? And they are defined from minus infinity to infinity, but their y values are from 0 to 1, okay? Tangent hyperbolic, that's similar to sigmoid, but uh, in the sense that their x is from minus infinity to plus infinity, but their range for y is like this, okay? Minus 1 to y, and their equation is actually like this, okay? And ReLU, they are having 0 when x is less than 0, and having x when x is larger than or equal to 0. So because of this point, this is not straight line, okay? So they can give us some nonlinearity, okay? But we are now frequently use this ReLU thanks to their good characteristic. And another thing we have to remember is these activation layers are differentiable functions. Their output is differentiable to the x because they are polynomials, right? Also same for this, but are this ReLU is differentiable? But why? I mean, first, is this differentiable? Please raise your hand if you think this is differentiable. 혹시 미분 가능하다고 생각하면 손 한번 들어볼래요? 왜요? 기울기가 1이라서? 근데 이 x는 0에서 define이 안 되잖아요, 미분값이. So the definition of differentiable means in every x, continuous x, their differentiation is have to be defined. Okay, but this function ReLU, their gradient is not actually defined for x is exactly 0, because in maybe you sorry. I will explain until here for today. So the other definition of differentiation is their differentiation from left side and right side, they have to be same. But here, sorry. Here in this direction, their gradient, their slope is actually 0. But in this direction, their slope is 1. Okay, so they are not same. From the left side, their differentiation value is 0. But from the right side, their value is 1. So they are not same, and their gradient is not defined. Okay, that's actually the characteristic of this value. So, but still we are using them inside the deep architecture. Okay, so how do you think this can be done?
Define when something
Hmm?
like in a way manually define derivative when something
Manually define derivative
at 0 to some number.
to some number. But which number? 0? But I mean, it's not continuous anyway. If you put 0 in the for x is equal to 0, it's not actually continuous to right hand side. I mean, for the values which is just right after the 0, that would be 1. Okay, but if you assign 0 to 0 for x is equal to 0, then anyways, that 2 pixels are not continuous. Okay, and that can make trouble, actually, but still. But I mean, this is kind of trick. Okay, so I mean, in computer, I mean, when getting the value, some intermediate response, I mean, that response, there's very low probability that that response will have exactly 0. Okay, so actually we are ignoring that specific point. Okay. So I mean, in practice, our response cannot be exactly 0, maybe. Yeah. So because of that, we are using this ReLU. Okay. And another important thing you have to remember, compared to the sigmoid and tangent hyperbolic, is they are anyways have to be in some layers in the deep architecture. And for example, they have to help to calculate some of the, let's say this is some f, okay, and this, okay. So they have to be stable when calculating this DLDF, okay. But thing is, for example, in this type of, when their responses are like this, okay, even though their x values are defined from -infinity to infinity, if their x values are becoming larger or less, their, how to say, gradient values are becoming too small. Okay, and the computer precision is actually limited, and they will regard some small values which is not 0 as 0. Are you guys agree with this? So I mean, this slope is not having 0 slope, okay? But I mean, for their inside the deep architecture, their x values are actually becoming larger, and there's actually no limit, okay? But their responses are becoming larger, then we can just have 0 gradient, maybe, okay? And this direction, that will be similar. And if we use tangent hyperbole, that is also similar, okay? So because of that, if the deep architecture becoming deep, you will later call some learn about this vanishing gradient phenomenon, which means gradient is becoming to zero, simply becoming to zero if the gradient value is very small. Okay. So actually for these ranges, the gradient values, this type of values are not stable, and even they are simply becoming to zero and making the entire gradient to zero. Okay. And because of that, the training is not becoming stable. Okay. So because of that, we prefer nowadays ReLU, because I mean for ReLU, they are providing us the stable gradient 1 for when x is larger than 0. And if x is less than 0, their gradient is just 0, right? They are giving us the fixed gradient, okay? Not if their x value responses are not exactly 0, then they can give us stable gradient. So this is giving us some benefit for training the entire deep architecture. So that's why we prefer this ReLU compared to the sigmoid and tangent hyperbole. Okay. Okay. So now actually we learned pooling, activation, and convolutional layer, and that's actually the first part of this entire architecture. So this network is composed of 2D pooling and activation. Okay. And in the middle, if the 2 dimensions are reduced, they are actually flattening the signal, okay, to make it as the 1-dimensional vector and apply MLP, okay, whose operator is like this, to map it to semantic class dimensional vector, okay. And after constitute this differentiable architecture, you can train this using the gradient descent. Okay. So, and the first part, we will call that as the convolutional layer because they are mostly composed of the 2D convolutional layers. And the later part, we call that as fully connected layer. Okay. And the first part, we observed that, thanks to the characteristic of the convolutions, they can transform the images, okay? And there actually, if we analyze how the convolution operations are transforming the image pixels, then we can observe that they are actually role as some feature extractor, as if we made the BOW, the bag of words representation for the whole image before, okay, to make the appropriate feature for the images. So anyways, the convolution layers, that is role as the feature extractor, okay? And the later part, as we apply SVM or machine learning classifier for the features extracted, this later part can be considered as the classifier, okay? The fully connected layers are, popularly, they are normally considered as some classifier, and the earlier part, the convolutional layers, are considered as feature extractor. Anyways, so this is the convolutional layer, and maybe from next class, this Wednesday, we will learn about how to implement these convolutional layers with the PyTorch code. Okay. Okay. Thank you, and see you this Wednesday. 네, 잠시만요.